Hello everyone, this is Amit here. Today I am going to talk about building a scalable API platform using GoLang. Here at Fox, I work as a director of engineering. Me and my team is responsible for taking care of the platform, which helps to serve live and on-demand content for millions of concurrent users. Serving live content has its own challenges, and your challenges becomes more difficult to handle, especially when you have millions of concurrent users watching the same content at the same time. Our platform helps to serve the events like Super Bowl, pay-per-view fights, WWE, and lots of other Fox Entertainment related shows. As part of this particular talk, I'm going to focus on playback portion of the overall API platform. Let's go over the agenda. First, we are going to understand what is playback API platform. And once we understand that part, we will go over the overall challenges which we had with our legacy API platform and why did we think that we should rebuild it. Once we understand why did we rebuild it, we will go over the details that how exactly we kind of handle this problem and how did we rebuild it. And after that, we will go over the results. Let's understand what is Playback API platform. Playback API platform at Fox is basically a group of backend services which helps to serve the live and what content for various Fox products at very high level. Apart from this, this also helps to provide us the streaming playback URL for the viewers. It also helps to capture the analytics for the clients. I would give an example of various analytics like start time, date time, or subscription status for a particular user. Similarly, this backend API also helps us to deliver the various metadata related fields for decorating the clients like title, description, show name, and various client related information. The most important task this particular backend system does is providing the backend related metadata to the players. And I'm telling this is most important because this directly impacts our revenue. This is one of the example page from the fox.com, but you can see here that you can, as a user, you can go and watch the videos from anywhere on the site. And you can go to home, you can go to entertainment tab if you're looking for the entertainment related stuff. Similarly, we have the sports and live TV and schedule. So as an user, you can go and watch live or on-demand content from anywhere. And you can expect probably similar kind of experience on dedicated sites for the Foxport and various clients. Here is the high-level architecture for our legacy system. This is important to understand uh, when it comes to the challenges. So as part of legacy system, you can see that we used to have one common playback API gateway, and we had bunch of internal modules. And these internal modules were either getting the data from Elasticsearch kind of data store or from some kind of external services. And then we used to merge all the response, give it back to the API gateway. In this diagram, it looks very simple, but actually these internal modules had very complicated business logic. Uh, Also, there were at least 20 to 30 different types of internal modules, which helps to get the data to the end clients. So what were the overall challenges with the system? As you could see, that whole system was kind of tightly coupled in a monolithic manner. And because of that, this whole thing was very hard to scale. Imagine where you have 20 to 30 modules running in same node application, and then you're trying to scale that application in case of high number of traffic. Other than that, as I said, the other challenge was like we had so much dependency on the external services, and these external services did not have any fail forward strategy. So in case if any external services is failing, which our API was depending on, our whole API used to fail. And because of that, as an user, you won't be able to watch the content. Another dependency, as I mentioned, was a dependency on the single data stores. Data stores like Elasticsearch are hard to auto scale whenever there is a high amount of dynamic traffic. One of the biggest challenge we had was like we did not have any caching in this whole system, and this was by design because live content in general are very dynamic in nature, so those are very hard to cache. We had difficult time releasing any new feature. As I said, we had 20 to 30 modules, right, as part of one application. So if you touch anything, it had potentially side effects on other parts of the system. And since the system was being used by lots of other products, we had very little scope to release any new feature at given time frame, as we had to be very careful. Another challenge was like even if we thought, that okay, we want to build a new API platform, but that how do we migrate to new API platform without any downtime? As this system was always live, we had so many events going on all the time, so we cannot shift the events just to migrate to the new API platform, right? So we had to come up with some innovative ways where we can iteratively launch or a new API platform while maintaining the legacy API platform also. Apart from that, we had other feature goals. At given point of time, we wanted to have the capability of supporting millions of concurrent users without any manual interruption. Since last year, our digital streaming viewership has increased significantly. And since you have high number of the users all the time on your platform, it doesn't mean that we should sit 24/7 for supporting this kind of system. Our system should be in such a manner so that if there is an issue happening, then it should be able to auto heal and then continue supporting or continue serving the contents to end users. And that should be our normal business mode. Apart from that, we also wanted to have the capability of serving at least 8 to 10 millions of concurrent users for any big events like Super Bowl or any important game at the NFL. Another feature goal was like to ability to handle the thundering herd in case of app crash or simultaneous ad breaks. Let me explain the scenario behind app crash, right? So in case of app crash, let's say if you have millions of concurrent users on your stream watching the content, and suddenly in this case, if your app crashes, then all these logged in users are going to retry to play this stream again. And if that happens, all these users are going to send a high amount of unexpected traffic to your backend system. So in this case, even if your backend system is trying to heal itself, it won't be able to heal because you have suddenly so much of traffic which cannot be managed properly, right? Um, and the same kind of thing may happen during ad breaks also. Ad breaks is a very normal scenario. Like as a user, whenever you watch any content, while watching the content, at some point of time, you will hit some kind of ad break. Uh, and when you hit the ad break, um, everyone is going to basically go to the backend system to grab the ad related metadata and helps the player in this case. But in this case, since everyone is logged into the stream and everyone is going to hit your backend system at the same time, you will also have a scenario like thundering herd in this case. So for both of these two use cases, we wanted to have a system where we could handle this kind of scenario gracefully. Even if there is any problem, the system should be able to handle these problems in such a manner so that users' experience doesn't interrupt. Another goal we had was to ability to support the game extension at any live event, right? As I explained, live events are basically configured for given time duration as we have the next program scheduled to stream. But in case of live game, whenever it goes overtime, we will have to go back and reprogram our schedule. And since we reschedule our program, This basically is going to cause lots of elements to be reset. And this particular event or this particular operation may cause a similar kind of thundering kind of problem, which I explained in previous slide. As I said, our goal was to basically, have a graceful degradation or ability to have graceful degradation. Similarly, we wanted to have the ability to support a robust monitoring, and at the end, we wanted to have a platform which should be resilient enough to for common failures or system outages or infrastructure outages. About how exactly we addressed those challenges. That's a story worth telling to the community. Let's go over those one by one. One of the main thing we targeted was dividing this whole system into true microservices. Breaking down the API platform into true microservices, we basically chose or we basically did that on three basic criteria. The first criteria was like, first let's look into what are the dependency from the external services, right? Since external services did not have any kind of fail forward, we have to have some way of monitoring those services without depending on the external services itself. We wanted to know in advance that okay, if there is any problem, then we should be able to take some steps at our end. Uh, Similarly, the same kind of thing with the internal legacy services. We knew that we cannot migrate everything altogether to new platforms. So we wanted to have some strategy where we can identify some internal module as internal legacy service, and then we can handle those as a dependency in different manner. Another thing we considered as a criteria here was dependency on the data stores like Elasticsearch, or if it is a DynamoDB or anything, right? And then treat those whole thing as its own service. But before we divided all these things into microservices, what was the strategy we came up to basically migrate these services to new services? Well, this look into some example here, right? In this case, you can see this is the start kind of a state, right? In this case, as a client, you will be hitting the existing service, right? Which will be like legacy playback services, right? And then what we did, first we start from this start state, we basically applied a proxy service pattern here, right? In this case, what we started doing, like we kept our legacy playback services as it is, and on front, we started introducing slowly Go-based proxy services. The job of the proxy services was nothing but talk to the client without impacting the client endpoint, right? And get the request parameters and pass it to the playback API, and then get back the response and send back the response to the clients, right? By doing this, we got lots of flexibility now, right? Which I'm going to explain in other slides. But this is a very strong pattern, and very useful pattern from the migration point of view. The next thing was we did started doing was like build new service and perform the testing. So in this case, what we did, like, so since we already had the proxy now, right? We had the capability to start building the new playback service, right? And in the background, based on the product dynamic traffic or the production log, we started doing the comparative testing. And this was not for a whole backend system. This was like each and small components which we were building, and we were kind of swapping with the new playback service. And once we had that, we implemented something called like feature flag, right? And then based on that feature flagging, we had the capability to canary to new service, right? and and just send a small amount of the traffic to new service, and then let legacy service keep serving the most of its traffic. And once we had that confidence, we basically move to actual new service itself. Once we had that, the next pattern we, as part of this whole strategy, was we realized was the breaker pattern. As you guys, as you know that circuit breaker pattern is very common pattern in case of microservices, right? Basically, this particular pattern helps you to build fault tolerant or resilient system that can give you, that can survive gracefully when your key services are either available, unavailable, or those are, failing, right? And as I explaining you here in this particular slide, the circuit breaker pattern was very useful for us, because now at the proxy level we could implement the circuit breaker pattern, and even if we were having problem from the legacy services, we could identify, yeah, there's a problem on these use cases, and then this is where we should kind of focus on. And the same pattern can be applied while calling the external services. And the same pattern can be applied while integrating with any internal services, or while integrating with any data stores. So suddenly, as soon as we applied a circuit breaker pattern for external services, it gave us lots of flexibility to monitor those services. In this case, whenever external services was not performing, or circuits were open, and then we could see, okay, this is the response, and based on that, we could implement our own fail forward kind of scenario for those kind of use cases. Once we implemented that breaker pattern, as I said, we had so much flexibility to control these things at our end. This is one of the example, from the circuit breaker pattern we used for the config, right? As I said, like for circuit breaker, we used Hystrix Go library here, and this is the sample config. As part of that config, you can see like we will configure our service name, like percentage of the error threshold, and if the service is external or internal, it was a flag. And then we also kind of like implemented our max concurrent request, which we could send based on service itself. And the same, there are other parameters like request timeout and sleep window kind of thing, right? So this is just the sample config in this case. And because Go is such a strong language, it had a very useful way of writing or caller service code using circuit breaker in a very simple manner. This is one of the example. As a developer, we did not have to write lots of code for calling another service, because we using GoLang's interface, we were able to abstract out most of the functionality used across all the microservices as part of different um, helpers. And as a developer, you can just pass your dependencies to these caller services, and then you can call your services. In this case, you can see like from the caller service, we just pass the context and some kind of argument which are a request, which a particular service expect, and then we just build the request path, and then we can send. As part of the circuit breaker configuration, we also implemented some kind of like retry, scenario for the default use cases in case of timeout or 500 on all those use cases, right? So as a developer, you didn't have to worry about implementing all these kind of things, right? Those were abstracted out, and you just have to pass those as dependencies. Okay, as a dependency for the timeout, I would like to retry this service, right? Sometimes you do not want to retry because the service cannot handle those kind of scenario, right? So those were like optional use cases, which as a implementer of the caller service circuit breaker, you can choose, or you can ignore those. And this is how once we had that as part of the same implementation, we were able to implement our monitoring dashboards also, which were based on the Grafana. This is how our overall circuit breaker based monitoring dashboard looked like. You can see like now after that we were able to track what were the duration of various calls we were sending out, right? What were the total number of the historics errors? What were the total number of timeout errors, right? And then similarly, the state of the circuit itself. Whenever anything used to go, orange or the red, in this case we knew that okay, this particular service is having problem, and then we need to take some action. So after implementing this particular pattern, we got so much flexibility to handle the fail forward kind of scenario. And this was much easier, especially when we started using this with the GoLang. In legacy system, we had a node based legacy system, and we had hard time opting in for this kind of pattern. But because of the GoLang's interface based approach, this became much easier for us to implement. Once we had the circuit breaker pattern in place, we started basically implemented the strategic caching kind of thing. In case of GoLang, um, um, uh, in case of GoLang, because of its concurrency features, writing caching totally made sense for us, right? And we wrote our own caching layer based on memcache, where we were able to implement the features like leaky bucket and the stale cache, right? Because of the leaky bucket, without doing lots of hard work, our cache, we were able to keep our cache warm all the time, and we did not have to put any much effort. And same thing applied for the stale cache, right? In case of any failure from the external services, we could rely on our stale cache, right? Where we could serve the content from our stale cache instead of like just waiting for external services to come back. And this is our strategic caching kind of implementation look like. As I said, like we were able to abstract out the whole caching as a different service and provide uh, or expose that to for other services, right? So in this case, our overall implementation look like okay, whenever the request is coming from the end clients, first thing a service will do, it will go and check into the cache, right? And if cache has the data, we will start serving the data from the cache. But if cache does not have the data, then we will basically go back to the origin, right? And we will get the data from the origin services, right? And then we will serve the content, and asynchronously we will also uh, send that data to cache so that next request can be served from the cache. And this is the example where we kind of implement it. As you can see in this case, like we did not have one ID or one request. We had lots of video IDs which we wanted to get the data for, and we wanted to serve the data from. Another interesting pattern we used in the Golang was the basically a single flight pattern. As I explaining you that various problems with a thundering herd, right? And to handle the thundering herd kind of problem, single flight is one of the very handy pattern you will see in case of microservices. So basically, single flight pattern is nothing but basically it provides to suppress all the duplicate calls, and it ensures that only one request goes to origin and get the data, right? So in this case, what we were able to do whenever we had the ad breaks kind of scenario where most of the requests were exactly same, and we wanted to get the data for all those requests. So what we did, like through single flight, we were able to get the data for one request. We warmed our cache, right, using that request, and then rest of the request were served through the cache itself, right? So in this case, we kind of like saved our origin to handle those many concurrent requests at the same time. Here is our single flight implementation looked like. It's very simple implementation, but as you can see, like, we are relying on SF group, which is a single flight group, and it passes its dependency to do, and then cache key, and and then it just returns the interface, right? In this case, other common pattern, but those were very useful for us in case of app crash kind of scenario. And those one of the pattern which we found useful was like, okay, implementing the API gateway based throttling to protect our external services which could not scale sufficiently. We basically relied on AWS API Gateway Throttling, um, and and this helped us to save us from that 100x traffic which we could receive during an app crash. Right now, in this case, API gateway layer itself was able to throttle all those clients who are sending unexpected traffic in case of any big incident happen. We also implemented the pattern something like despite like uh, disable the auto retry and let the clients retry. Basically, client initiated retry in case of throttling limit exceeded. Apart from other patterns, we also came up with some kind of ideas for the implementing partial versus major failures, right? So we started calling those Defcon mode, right? In this case, Defcon 5 was like a normal mode where all the features will work, or everything will work. But in case of major failure, or in case of any portion of our system is down, we had something called Defcon 0, right? Where we will turn on this flag without restarting our services, right? And by default, we were able to serve the traffic in this particular Defcon mode. Results. Once we had all the patterns implemented, the results were very exciting, and one of the biggest result we started seeing out of this was like we had an ability to scale our system to at any level. The Ghost microservices were so light that we did not have to depend on any other kind of external dependency. We were able to scale our services independent of anything else. And this is what it looked like from the service response point of view. As you can see, like during Node.js, with very small amount of traffic, a simple service used to take more than 500 milliseconds. But after GoLang, it basically came down, under 50 millisecond, which was incredible because that helped us to save lots of things in other areas, like AWS ECS container count for the service was reduced by 50% at least. Similarly, we had the ability to release any microservices feature um, faster now, because now we could just release our services independent of any other services without impacting them. So our ability to release any feature you know was very fast. Similarly, this also helps us to develop a better monitoring tools, as I was showing one of the Grafana dashboard example. Now we can serve most of our content in USD 4K. Nowadays, you will see lots of NFL content. In fact, last Super Bowl was served in 4K. In the end, we have a highly successful team, and our team looks like this. This is one of the small moment from last year's Super Bowl event. Um, And this is the end. By the way, if you guys want to be part of our team, then we are hiring. Please feel free to reach out to us. Thank you.